Welcome back, everyone. In this video, we're going to talk about how to do double integrals in polar coordinates. So we're going to talk about just a quick review of what polar coordinates are, and then we're going to do double integrals in polar coordinates. We're going to see how to do integration in polar coordinates and how to change from Cartesian coordinates to polar coordinates. Let's begin first with a review of what are polar coordinates. So if I have a point in the Cartesian plane, so here is my point x naught, y naught, then I can describe that point in a different way. This point in Cartesian coordinates is just described by what the x coordinate is and what the y coordinate is. But instead of that, what I can do is describe it in a different way. I can measure the distance r to the point, and I can measure the angle with respect to the x-axis. Now, I can, with those two measurements, I can describe what the point actually is. And given those two measurements, I can, in fact, retrieve the point itself, because remember that by trigonometry, this distance and this distance are given by, this is given by r cosine theta, and this is given by r sine theta for this point. So what I'm getting is that x naught is r cosine theta, y naught is given by r sine theta, and also, by the way, r itself is given by, it is the square root of x squared plus y squared by Pythagoras theorem. So what that means is that r squared is x squared plus y squared for the point x naught, y naught. Okay. So the changing Cartesian coordinates to polar and vice versa is going to be the following. We're going to replace the Cartesian coordinates. We're going to talk about points in terms of the r and the theta, and see if we can integrate with respect to r and theta instead of with respect to x and y. But before we go into integration, let's try to describe regions that are in regions in the plane. Let's try to describe them in polar coordinates. These regions are, for example, this is going to be, let's call it R1 and R2 to distinguish them. So this one is R1 versus this one that is R2. In R1, we are talking in Cartesian coordinates. Those are the points x, y that are inside the circle. So those are the points with x squared plus y squared is less or equal to 1. How would I describe this in polar coordinates? Well, first of all, the angle. Let's put a point here, and let's put the theta and the r. The angle, so these are going to be points given in polar coordinates, such that the angle can go the full circle. So the angle can be anywhere between 0 and 2 pi, while the radius, you see, the radius can only be between 0 and 1, so it doesn't escape the circle. So the radius itself is between 0 and 1. So this is the description of R1 in Cartesian coordinates versus this is the description of the same region in polar coordinates. Let's try to do now region 2. So let's try to now describe R2 first in Cartesian coordinates and then in polar coordinates. In Cartesian coordinates, those are points that are between the circle of radius 1 and the circle of radius 2, because this is a 4 right there. That is the square of the radius. So the radius is 2. So it's between a circle of radius 1 and circle of radius 2, but also such that the y coordinate is positive. Okay. So first of all, we need it to be between the two circles. So x squared plus y squared have to be between 1 and 4, and the y coordinate has to be positive. Okay, so that describes that region. So let's see if I can describe it in polar coordinates. So these are going to be r theta, such that, first of all, the angle, you see the angle here goes from 0 degrees all the way to pi degrees, but it doesn't go between pi and 2 pi. So the angles, the possible angles, have to go between 0 and pi, and the radii go between 1 and 2. They also do not go between 0 and 1. So the radius itself is between 1 and 2. By the way, remember that x squared plus y squared is equal to r squared. So I could have put that r squared is between 1 and 2, but actually what I want is the radius itself between 1 and 2, to be more precise. So this is now the description of this region, R2, in polar coordinates versus the description of the region in Cartesian coordinates. So how are we going to do double integrals in polar coordinates? So in polar coordinates, suppose I want to integrate over this region R, which is some circular sector. What we're going to do is just like we did with the Riemann integral. We're going to subdivide it in rectangles, but I'm going to use in my favor the circular symmetry, or the symmetry about the origin, and divide the entire region into circular sectors, into small circular sectors, and then the integral of the function with respect to x, y, and the area. Well, we know what x is. X, for each one of these squares, I'm going to pick a little point, and it would be, well, I know what the translation of x is. X is r times cosine of theta for that particular point. Y is r sine theta for that particular point. But what is the area of such a region? If you expand this, the area of such a region will be approximately, the area will be the length of the change in radius times the change in angle, except that when you're calculating the area of a circular region, it depends how long is this radius and what is this change in angle. So this length here will be the change in angle times the length of this radius. And then if you multiply this by the dr, then you get an approximation of what is the area of that square. So instead of dx dy, we actually have to multiply by a different conversion factor, which is r times delta r times delta theta. And this little conversion factor is the conversion factor that we need to go from Cartesian coordinates to polar coordinates. And every integral, when we transform it to polar coordinates, there is going to be this extra factor of r that we have to add in to factor in the fact that these boxes are not just rectangles, they are really circular sectors. So here is the theorem. If we have a function that is continuous on a polar rectangle R, so a polar rectangle is a rectangle that is such that the radius is between A and B, and the theta is between alpha and beta, which is what's happening here. The radius is between radius A and radius B. The angle is between alpha and beta. So this is what we call a polar rectangle. And then the integral of the function on this region will be the integral in polar coordinates, dr d theta. The r is going from A to B, from radius A to radius B. Theta is going from alpha to beta. But we have to substitute x. Remember that x is equal to r cosine theta, y is equal to r sine theta, so that is the transformation here. And we have to multiply by the transformation factor r that transforms rectangles in here into circular regions over here. So let's see some example. Let's start by finding something that we already know, finding the area of a circle of radius 3 using double integrals. Well, I know what the area of this circle will be. Let's call first the region R. In this case is going to be a circle of radius 3. I know what the area of my region is. I don't need double integrals to tell me that. It will be pi r squared, so it will be 9 pi. Great. But let's try to do this using double integrals. And remember from the previous video on properties of integrals that if I want to compute the area of a region, then what I need to do is do the double integral over the region of the function equal to 1 and then compute the integral there. So here I could try to do the integral of my region. Here is my region. Let's draw. My region is a circle of radius 3. So I'm trying to do an integral over this region in some way. And I can try to do that in Cartesian coordinates as a, perhaps I could do it as a here's 3, here's minus 3. I could do it as a type 1 integral. This is going to be 9 minus x squared, the square root of 9 minus x squared, the square root of the minus square root of 9 minus x squared. That could be that I do just the integral in Cartesian coordinates. This could be the integral from minus 3 to 3 dx, integral from minus a square root of 9 minus x squared, the square root of 9 minus x squared of 1 dy dx. But instead of doing that, let's rewrite this integral in polar coordinates by writing r as a region in polar. So the region in polar here is in r and theta. The radius is going between 0 and 3. So I'm going in radius between 0 and 3. And theta can go any angle between 0 and 2 pi. The radius is going from 0 to 3, but the angle can go from 0 to 2 pi. Okay. Now, what is the function that I'm integrating? Is just the function 1. And remember that in principle, I have to evaluate, look at the formula here. I would have to evaluate the function, which is the function 1, at r cosine theta, r sine theta. But in this case, it's just the function 1. So I'm going to do the integral in angle. I'm going from 0 to 2 pi. In radius, I'm going from 0 to 3. And now the function 1 evaluated at r cosine theta, r sine theta, but this is just constant equal to 1, so that is just 1. And now I have to multiply by the conversion factor of r, and then what is the order of integration? dr d theta. I can figure that out too because this is the r is going from 0 to 3, so that is the first one. So I have dr is the integration in the inside is with respect to r, and then the integration outside is with respect to theta. Okay, so I have translated my integral, this integral, into polar coordinates successfully. So it's that integral. So I have to find the integral from 0 to 2 pi of the integral from 0 to 3 of r dr d theta. Okay, so I can do that. First, we integrate the inside. So the integral with respect to theta is just the same. But the integral inside, the integral of r, will be r squared divided by 2 with respect to r. And I'm going to evaluate between 0 and 3. That is, let's just still integrate with respect to theta without any changes there. And the integral of r squared divided by 2, r squared divided by 2 evaluated at 3 gives me 9 divided by 2 minus 0 divided by 2. So now I have to integrate between 0 and 2 pi, just the integral 9 divided by 2 d theta. Okay, that is just a constant. 9 divided by 2 is a constant. So when I integrate with respect to theta, I get 9 divided by 2 theta. And I'm going to evaluate between 2 pi and 0. That is 9 divided by 2 times 2 pi minus 9 divided by 2 times 0. And well, this will just be 0. And here the 2's will cancel out. And what I get as an answer is 9 pi, which is precisely what I got before. That is the same as pi r squared. So yes, this is correct. The area of a circle of radius 3 is 9 pi. I can do exactly the same thing for finding the area of a circle of radius r. So if I want to find the area of a circle of radius r, I would integrate 1 over the circle of radius 1, so points x, y, such that x squared plus y squared is less or equal to r squared. And I can translate this to polar coordinates, so this will be, in fact, equal. So let me just write equal to the integral from 0 to 2 pi. Integral for this region, let's just write the region quickly here in polar coordinates. The theta goes between 0 and 2 pi, and the radius goes between 0 and capital R in this case, because I'm integrating the area of a radius of a circle of radius capital R. So the little r will go from 0 to r, and I'm integrating the function 1 times the conversion factor r, and then times dr d theta. Now I can proceed with my integration. The integral with respect to theta, still I'm not going to do anything to it, but the inside is the integral of r dr, which is r squared divided by 2 between 0 and capital R. That is the integral from 0 to 2 pi of r squared divided by 2 d theta. And that is constant. R squared divided by 2 is constant with respect to theta. So when I integrate with respect to theta, I get r squared divided by 2 theta between 0 and 2 pi. And when I evaluate theta at 2 pi, I get r squared divided by 2 times 2 pi minus r squared divided by 2 times 0 times 0, not theta. And the final answer is that this is just 0. The 2's cancel out like before, and I get pi r squared. So the circle of radius r has area pi r squared, as we already knew. Let's do another integral. This time I'm going to integrate a function 3x plus 4y squared over the region in the upper half plane bounded by the circles radius 1 and 2. I know what the region is. We drew it before. So this is the points r theta in polar coordinates, such that we have the radius is between 1 and 2. And theta, because it's in the upper half plane, it has to be between 0 and pi, because this region was the region that we had before that looked like more or less like that. Okay, so what is the integral over r of 3x plus 4y squared dA in polar coordinates? We'll have the bounds on theta, which are between 0 and pi. The bounds in r are between 1 and 2 of 3 times. Now, every time I see my x, I have to replace it by x is equal to r cosine theta. So this is 3r cosine theta uh, plus 4 times y squared. Y is r sine theta in terms of r and theta squared. And I have to multiply the whole thing, the whole function. I have to make sure that I multiply the whole function by my conversion factor of r, and then that will be dr d theta. If I simplify this, I get the integral from 0 to pi, the integral from 1 to 2. Multiply through the r, I get 3r squared cosine theta plus 4r squared times another r is r cubed. So I square first and then multiply by another r. I get r cubed sine squared of theta dr d theta. And with respect to r, this is not too bad because this will be the integral from 0 to pi of, this is r cubed cosine theta plus r to the 4 sine squared theta d theta, but now I have to evaluate r between 1 and 2. And I have done this math separately, and I get the integral from 0 to pi of 7 cosine theta plus 15 sine squared of theta. When you evaluate at 2, subtract the value at 1, you get this integral in theta, which I now can try to work out. How are we going to solve this integral? Okay, we continue here. Remember that to integrate the square of sine, what we use is this equality. So I can actually rewrite this as the integral from 0 to pi 7 cosine theta. I will be able to integrate cosine theta, no problem. But this is plus 15 divided by 2, 1 minus cosine of 2 theta d theta. And now I can integrate that. The integral of 7 cosine is 7 sine theta, and the integral of 15 will be of 15 divided by 2, that's 15 divided by 2 theta, and the integral of minus cosine 2 theta, that will be minus 15 divided by 4 sine of 2 theta. Evaluate that between 0 and pi, and the final answer is 15 pi divided by 2, and that is the integral we were trying to compute. This integral over that region, we translated it to polar coordinates to find this value. Okay. All right. Let's do some other examples. In this case, I'm going to do a double integral in some region that they are not telling me exactly what the region is. But the problem now is that I'm going to translate this region first into, I want to see what it looks like. And once I know what region I'm talking about, then I'm going to change it into polar coordinates where it's going to be easier to work with. So first of all, what is that region? The region is going in x between minus 1 and 1. That's easy enough. Minus 1, 1. And then above it is the function y is equal to the square root of 1 minus x squared. So we're going between y equals 0, that's the x-axis, to y equals the square root of 1 minus x squared. But this, if you square both sides, this is y squared is 1 minus x squared, or that x squared plus y squared equals 1. So this graph of this function is no other than the circle of radius 1. So we are actually integrating this region right here, which has a very nice symmetry about the origin. So it has a nice circular symmetry, and it's better expressed. This region is better expressed as in polar coordinates, it's simply the region that the angle is going between 0 and pi, and the radius is going between 0 and 1. And we're integrating the function is x squared plus y squared. Now, now I can, if this is my integral, I can translate it to polar coordinates. I'm going to integrate over that region in polar. So it goes between 0 and pi, between 0 and 1 of the function. But the function, notice that this is r squared. Remember, the translation is that x is r cosine theta, y is r sine theta, but r squared is x squared plus y squared. So we are, in fact, integrating r squared. I have to multiply by my conversion factor always times r, and then dr d theta. dr d theta. So I'm integrating then, the integral is the integral from 0 to pi, from 0 to 1 of r cubed dr d theta, and that's easy enough. That is the integral from 0 to pi of r to the 4 divided by 4 between 0 and 1 d theta. That is the integral from 0 to pi of a fourth d theta, and that is simply a fourth theta between 0 and pi, which is pi over 4 when we're all done. So that is the answer, is that is pi divided by 4, while without the polar coordinates, this integral would have been quite complicated to do. Let me do one last example, which is find the volume of the solid bounded by z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. So what that means is the following. I have the z equals 0 is actually the plane z equals 0. So this is z equals 0. And then the paraboloid, that paraboloid has a height of 1 and is a paraboloid that opens down. So it is something like this. And I want to estimate, I want to compute the volume under the paraboloid and above the xy plane. So this is my function. So this is my function f of xy. And I want to figure out what is that I'm integrating over. So first of all, what happens when I do the intersection of this with the plane z equals 0? What I get is 0 is 1 minus x squared minus y squared, which implies that x squared plus y squared is equal to 1. So the intersection down here, that is x squared plus y squared is equal to 1, and I'm computing the volume above all the region captured by that circle. So my region is the circle. The region I'm integrating over is the circle. X squared plus y squared is less or equal to 1, which in polar coordinates is r theta. The radius, or the theta, is going all around to 2 pi, and the radius is going up to 1. So the integral, which would be the integral over this region, over this circle, of 1 minus x squared minus y squared dA in polar coordinates will be the integral from 0 to 2 pi, the integral from 0 to 1 for r. And then what is this function here? This is 1 minus x squared plus y squared. But again, x squared plus y squared is r squared. So this is the integral of 1 minus r squared times my conversion factor r times dr d. So we are trying to do this integral, which is also the integral of 0 to pi, integral from 0 to 1, distribute the r, and I get r minus r cubed dr d theta, and that is the integral from 0 to 2 pi. That is the integral of r is r squared divided by 2. The integral of r cubed is r to the 4 divided by 4 between 0 and 1 d theta. That is the integral from 0 to 2 pi. At 1, that will be a half minus a fourth. And at 0 is just 0. So it's this integral, which is in fact a half minus a fourth is just a fourth. So it's the integral from 0 to 2 pi of a fourth d theta, which will be theta divided by 4. The integral is 0, theta divided by 4 between 0 and 2 pi, which will be 2 pi divided by 4 minus 0 divided by 4. So the answer is pi divided by 2. And that is the volume that we were looking for is this number. Okay. So next time, we're going to be looking at integrals in for triple integrals. So if we are integrating functions of 3 variables, and then we will do things like spherical coordinates and